line. As Betty was introducing me there, I did my BSc in physics, and later on I did a master's in applied maths, both in UCC. And I moved to Dublin in 2001, and I got a job in the Dublin Institute for Advanced Studies 2014 as a seismic data analyst through the job bridge program. I was unemployed for quite a while. I was a musician, and so naturally I didn't have a job. I was playing gigs, and eventually the dole told me that I had to get off it. So I found a job as a seismic data analyst, a 9-month position, and I had never heard of this before. And then it sounded interesting. I downloaded a book on some of the basics of it, and I found that it was very, very similar to what I had been studying in my master's thesis. So I straight away just kind of dove into it with 2 feet. I really enjoyed it, and I haven't looked back since. Very enjoyable subject, I find, very rewarding intellectually. So I've been in DIAS for 6 years. Currently I'm a seismic network analyst. So I'm a data analyst for the Irish National Seismic Network, and I also am a data analyst for various other projects that we do in the geophysics section in DIAS. And so I work for the professor of geophysics and also for the director of the seismic network. And so a lot of what I spend my time on is seismicity of Ireland, detecting earthquakes, and also then trying to derive what can we derive out of that. So a lot of it is very technical, so I'll try and keep most of that out of it and try and keep it quite simple tonight. So I haven't timed the talk exactly, but I think it should be about 40 minutes, maybe around that, maybe 35, 40 minutes. Okay, so I'll plow ahead. So the next thing I should be able to do is move. Oh, so I'm not seeing this. 1 second there now. I'm gonna stop share for a sec, and there we go. Okay. So basically, the topic of this talk is going to be about earthquakes around Ireland, detection, location, what they can tell us, a little bit about. So the first thing we're seeing here is on the left is the map of basically detected Irish earthquakes from 1980 to present. So that's 40 years worth of earthquakes. And if we were to count them, it's about 370, I think, altogether. And in most locations in the world, if you were to ask them how many earthquakes have you had in the past 40 years, it would be an awful lot more than 370 for various different reasons. But one of them is basically how many seismometers have been out. Another reason is how many earthquakes are actually happening. So it turns out Ireland is quite low seismicity, but you don't actually know what it is until you start putting out instruments. So again, the topic of what we're going to try and do tonight is go a little bit over detection, location, what causes them, why do we study them. The first thing you might notice in that map of Ireland with all those circles on it is why are there no circles in the actual country? Why are they always at the edge or in the Irish Sea? And again, that's a very interesting question. The red lines on this map indicate faults that we know about, and or a better way to describe it would be the surface projection of kind of faults that actually are in 3D, not in 2D, but that's then projected onto 2D. Most of the seismicity, as you can see, these circles tend to occur offshore and not actually on the island itself, which is quite interesting and poses a challenge from the point of view of monitoring and detecting and locating. The sizes of these circles indicates their magnitude. So we'll be seeing this map later on with more detail. But the larger the circle and the darker the color means the stronger the magnitude. They tend to happen offshore to the west. And the lighter the color, the smaller the circle, then these are smaller magnitude events. So the largest one we have there is magnitude 4, which occurred off the coast of Mayo in 2012. And everything else is smaller than that. So orange is magnitude 2 and yellow then magnitude 1. White is undetermined, but probably quite small. Okay. So first thing, I suppose, is the Irish connection to seismicity, seismology, and the actual word itself, seismology. So this is this guy, Robert Mallet, who's from Dublin, I think, son of an engineer, and he coined the term seismology and also several other terms associated with it. So epicenter, isoseismal map. This was him, and so he did quite a few experiments in South Dublin, Liney Beach, Dalkey as well. So he would have had explosives, and he would have detonated them on the beach and seen how long it would have taken for the shockwaves to reach him at various different distances. And as I said, he was an engineer, and he was also involved in the Crimean War, I think, and he was building mortar rounds, so he was pretty well familiar with explosives. And then from my time in UCC, I remember the computer scientists always talking about George Boole being the father of computer science. So in Trinity or in Dublin Institute of Advanced Studies, we have the Mallet as the father of seismology. Okay, just again, if you're not familiar with the technical term, epicenter is kind of the location on the surface of the Earth where above the hypocenter where the earthquake actually occurs. So actually, earthquakes, they occur at depth, and so then the epicenter is basically just directly above the hypocenter. Okay, so the first thing is about why earthquakes happen, and basically we come across faults, these discontinuities in rock where you can have motion, and they will slide against each other, and they can, with frictional forces, they can basically stop it from sliding until stress, which is stress is similar to pressure, but with a direction associated with it. And essentially, you can eventually have pressure so great that two large sections of rock will eventually move past one another, greater than the frictional forces. And what happens then is that you get a release of energy. And so if I press this, we should get a little animation. Yes, we do. We have stress building up, and then waves radiate outwards. And so very much like when you speak in air, you have sound waves moving out. When you have disturbances inside solids, you get seismic waves moving out. One of the big differences, though, with air or gases and liquids in general and solids is that in air you only have one type of motion, one type of wave, but in solids you have more than one. Okay. So our next map here is, again, map of the world with these tectonic plates on it. And so one of the amazing things about seismology, which we'll show later on, it's about 1960s onwards. It's been a global effort to monitor earthquakes. And so these have then eventually ended up mapping out the, as we know now, the tectonic plates. So again, here's global earthquakes above magnitude 5, I think. And they pretty much tend to line up where these plate boundaries are. That's how we know about these plate boundaries. On this map, the color coding, the red indicates that they're close to the surface. And then as we get in towards yellow and then towards green, we're going, these are earthquakes that are happening deeper and deeper and deeper. And you'll notice on this scale, in the top right, if we use a mouse, we can see that there's 700 kilometers seems to be the maximum depth at which we have these earthquakes occurring. And I think at below 700 kilometers depth, I think the temperatures are so great where you don't have the kind of forces needed to generate earthquakes, that there's it's a lot more fluid at that temperature at those depths. And the vast majority of the large earthquakes above magnitude 5 do tend to occur along these plate boundaries. And now here in this image, again, we have showing the plates again and their motions. And so we have at the bottom of this, we've got 3 different types of colors indicating the boundaries between the plates. So we have green for divergent, black for transform, and purple then is convergent. And convergent then is where they have basically two plates moving into each other, and one will eventually go underneath the other. The phenomenon of subduction. And divergent is then where they're in the opposite they're moving away from each other. And then transform then is more horizontal motion. And if we, for example, along the mid-Atlantic ridge, we can see that it's marked in green here, and so this is divergent. If we go back here, along the mid-Atlantic ridge, we see most of the earthquakes are all red, so they're not happening at depth. Now, one of the problems with detecting earthquakes in the mid-Atlantic is that it's very few places to put a seismometer. But if we look more at Japan, along here, we can see there's an awful lot of green, and say down around New Zealand as well. And on this map, we can see Australia and New Zealand. We have these purple lines. This is the convergent plate boundaries. Another point to make is that within the actual plates themselves, the movement is not uniform. And so this can lead up to build up in stress or differences in stress. And these can then give rise to what are called intra-plate earthquakes. So away from plate boundaries, we get earthquakes happening as well. And basically, whenever you have faults, you generally will tend to have them. But another reason for why we get earthquakes, this is more, I think, related to do with Ireland. Again, not an expert on this, but is this phenomenon of post-glacial rebound, that there was a large ice sheet covering, particularly perhaps the north, and certainly in Britain, I think, as well, in Scotland. And the removal of this ice layer in a time scale, on geological time scales, it happened very, very quickly. And so once the ice layer has been removed, then we have kind of a rebound of the Earth then. And so this can also, again, give rise to interplate earthquakes. Okay, so now I might get on to talking a little bit about detection and location. So again, now I've shown that map of earthquakes again, but this time we have a scale on it, and we also have thrown in some stations on it. These black triangles are seismic stations, and grey triangles also seismic stations. Black triangles are the stations of the Irish National Seismic Network currently operating, and grey triangles are those of the British Geological Survey. So on the island of Ireland, we have 7 stations then that basically monitor 24/7 and transmit data in real time. And that's it's quite a big distinction. We'll talk more about seismic networks a little bit later on, but these are the stations that transmit data in real time that allow us to locate and detect things in real time. And again, the scale is present on this. So again, red being the largest magnitude, and 4 is the largest magnitude we have occurring off the coast of Mayo. But and then it's kind of hard to see, but in Donegal, up around here, we have a cluster of events there, and actually that's where the vast majority of the 372 earthquakes I was talking about earlier on, that's where the vast majority of them occur, except they're all plotted on top of each other. So it only looks like there's a couple of circles, but there's lots. They're all sitting on top of each other. This is the place where they happen the most. Okay, so this is now kind of an illustrative video to show you the propagation of waves through the Earth as, say, an earthquake happens. And sites A, B, C, and D we can consider to be seismic stations with a seismometer recording. And down here on this little graph here, we will show a kind of a seismogram evolving in time as the waves propagate through the Earth. So we get several different types of motion. We get motion which is along the direction of wave propagation and perpendicular to the direction of wave propagation. So these are called P and S waves. We also have waves that propagate along the surface, and they're just called surface waves. So let's play this video. So down here we have an earthquake near station A, and then here we select a few different ray paths, and we show on the seismogram basically what the seismometers will record. And again, the color coding, red indicates the P wave, which will arrive the first, it travels the fastest, and the direction of the disturbances takes place in the direction of motion. The S waves are in blue, and the disturbance takes place perpendicular to the direction of motion. And the surface waves travel along the surface of the Earth, so they have a longer path to go to. They also travel more slowly. And that's generally what we observe for earthquakes. but I'm going to show you stuff from Ireland where they're kind of small earthquakes. So again, the maximum magnitude was 4, so most of what we record is smaller than that. Okay, so this is a seismogram, an actual seismogram of an event from 2012. This was the largest on-land earthquake that we've recorded, magnitude 2.5, and it occurred in Fanid Peninsula. So that's, I guess, just it's the next peninsula to the left, or to the west of where Buncrana is. So this is showing many seismic stations from around Ireland and Britain, and I've lined them up so that the seismogram on the bottom shows the closest station, and basically these are increasing as you look up. These are the seismographs produced by stations that are further away from this earthquake. And the idea is about trying to be able to recognize when the signal starts. And so if I move on to the next slide, I put in these red markers, and these red markers indicate approximately where the P wave would arrive. This is the first motion, and we can see that on all these, most of these seismograms, we can see that after this begins, there's a second lump everywhere, and this lump gets further and further away from this red markers as we go further and further away. So these this will be the arrival of the S wave, and I haven't marked it on the first station because it's actually very hard to determine where it is. What we will notice is that the time difference. So again, sorry, on the x-axis down here, we're showing time in seconds. So this is a total of 80 seconds. This is time measured from when the earthquake would have started. So within about 2-3 seconds, it would have hit the station IDGL. So it's very, very close to it. And we can see that the time difference between the S and the P on any of these stations, as we move further and further away from the earthquake, gets larger. So this also tells us that the P and the S, they move at different speeds, the P being faster, the S being slower. Okay, this is to demonstrate the principle of how you would locate an earthquake. There are many different ways, several different ways to do it. This is quite a simple way to do it. This is taking, again, a real example. This is from last year. It's located in Donegal Bay. And actually, interesting about this, I just landed in Vienna at the time. I was going to a conference in Vienna. And when I got off the plane and turned on my phone, I got a text message from the computer system at work saying that there was a magnitude 2.4 earthquake, and they gave the coordinates locating somewhere and looked like Donegal. And so when I got my laptop and looked at it, there it was. It was a lovely earthquake. That I think it was the first that had happened that year, and I so happened that I wasn't even in the country at the time. Disappointing. But if we look at this seismogram in the center here, we can see this station here, we have a P wave and then an S wave arriving after it. And so maybe measuring the time difference between the P and the S, that gives the constraint on how far away from how far away from that station this earthquake would have occurred. And here we have a rule of thumb that whatever that difference in time, multiply it by 10, and you get the distance in kilometers. That's where the epicenter is from that station. But only on one station, that means it can be anywhere at it. We have no idea what direction. So it's basically just telling us how far from that station it is. On the station here, we can also do the same thing. So this is down here. And we get a larger time difference. And so then I plot a second circle. This third station, we have an even larger time difference still, so we can then plot a third circle, and roughly the intersection of these circles is where we would expect our earthquake to lie, which is telling us somewhere here, but the actual location is there. So it's a rough way of doing it. It's not actually how we do it in our in the national network, but this is kind of an illustrative way, a very, very simple way to do it. But it of course requires where do they get this multiplied by 10 from? It requires some knowledge of the speed at which waves pass through the earth. Okay, this is a little bit more advanced now. generally how we actually do it is that we will have what's called a velocity model. And so this is what's being shown in this graph here. Along the x-axis, we're showing velocity, and on the y-axis, we're showing depth. So then this is basically what we've said is the structure of the Earth is like this. As we go down from 0 kilometers depth down to 20 kilometers, P wave will have a certain speed, almost close to 6 kilometers per second. And then there will be a jump down to roughly 35 kilometers. From there, it'll be a bit faster. And from 35 kilometers onwards, it gets much faster, 8 kilometers per second. And there will be a similar profile for an S wave. And so these ones in blue is basically a global average for the planet that's quite rough and quite coarse. But it's basically saying that as you go down through the Earth, there is one layer until 20 kilometers. There's a second layer down to 35 kilometers. And then there was a third layer from 35 that goes down quite far. So for all the people that are geologists here, this is a horrific distortion of reality, but it's very, very simple. We actually get away with it for locating earthquakes. These red lines then is what we derived in DIAS. I was one of my supervisors from a project several years ago. He came up with this. It's a slightly more refined model for Ireland. And it basically allows us to get a slightly more accurate location of things. So this involves then measuring these P and S arrival times and then calculating, looping through many different types of many locations and seeing which one is the best fit. That's actually how it's done. Up here in the top right, this is the location of the earthquake when located with a simple global model. And down here on the map below it is a relocation with a slightly more appropriate for Ireland model. And so it pushed it a little further to the west, and also changed depth of it a little bit. But the depth of earthquakes is the hardest part to constrain when we're locating them. It is much easier to get an epicenter than to get an accurate measure of depth. So a lot of the time when people report earthquakes, they tend to report it as depth of 1 or depth of 10. Or maybe of 20 in those kind of blocks, because the error on the depth can be quite large unless you have very, very dense seismic network. And in most cases, we don't have that. Okay. So this is a little schematic telling us about basically how our national network works. So we have seismic stations. And so in this map up here, we see this yellow triangles at the locations of the current seismic stations of the Irish National Seismic Network. Again, remember there was one more on the Antrim coast operated by the British Geological Survey. So we basically get data fed from these stations. So we have seismometers inside these huts that they're built onto the actual underlying bedrock. So they have very good connection with the underlying rock. So the signal is quite good. And so this data then is then transmitted from 3G to our data center in Dublin, and all the screens all there. This is the office I actually work in, and I actually only use 2 screens at any given time, but it just looks quite nice having lots of these screens for show. Once the data comes in, then we have software that works on processing the data, and this is analyzing the data for any changes in the signal, and from changes in the signal, then we would expect is there anything that's causing those changes, and if we see a pattern of changes in signals across various different stations, and this is then when we start to get interested. And so we have automatic routines for doing this. But we also manually look at data as well. Sometimes a lot of the time you don't catch everything, so it's very important to always be manually observing, especially for us. So just a little bit more about the evolution of the seismic networks in Ireland. So if we go back to 1977, so this is before I was even born, the seismic network looked like this, and so the station VAL, I think, was set up with conjunction from GFZ, a large German research institute in geophysics, and we have some stations here on the East Coast, and I think they were transmitting. I'm not sure if they were transmitting in real time. Perhaps they had telephone connections. I'm not sure, but it was pretty sparse. Flash forward then to the mid 90s, and there was another station built into Dublin Mountains, quite close to the N11 actually, but just south of the city. And this was again built by GSZ, I think. And then we flash forward to 2011. Then we have these permanent seismic network stations. And so these were all built in 2010, 2011. And so this is now the current state of the Irish network. And so these all transmit in real time. Okay. So this map now shows us that when we're analyzing data, again, we remember that we don't just have the Irish network. We also have plenty of stations in Britain as well, in the Irish Sea. So these stations also kind of contribute to monitoring seismicity as well, because seismic signals, just because they're in a different country, doesn't mean that they're not important. So an awful lot of the stations that are situated along Western Britain is very, very useful for locating earthquakes in the Irish Sea, or on the eastern seaboard of Ireland. They're able to constrain the locations of it. Whereas to the west of Ireland, there's nothing until the mid-Atlantic ridge. Even if there's anything out there, to Iceland, and that's it. So there's nothing to the west of Ireland where you can, build a land seismometer. So detecting events like this is certainly a challenge. And so, but that's not the full story of the seismic networks in Ireland, because we have many temporary networks or short-term networks. So now this map on the right tells us kind of basically what's been like for the last 10 years in Ireland. So in the last 10 years in Ireland, since 2010, we've kind of had an explosion of seismic networks. And so all the different color coding, it tells the different projects. So the INSN is the Irish National Seismic Network. The yellow squares is the BGS, the British Geological Survey. The blue circles is a project called WaveOp, started in 2011, UCD, and then was brought to DIAS as staff members came from UCD to DIAS. And so Professor Chris Bean was originally UCD, and most of my colleagues in the INSN were also UCD as well, until they came to DIAS about 5 years ago. Ireland Array is a long-term project as well, run by Professor Sergei Lebedev in DIAS. ISLE is a project that began in 2002, I think, and it still currently has a couple of stations out there. SimCrust was a network that began in 2012 to monitor seismic activity in Donegal, and it finished up in the end of 2019. So a lot of these stations are still actually out there. Not all of them have been out there at the same time, but there's been quite a lot of seismic stations in Ireland from which to analyze data. And so it's not just the 6 stations of the Irish National Seismic Network we're able to do analysis with. The main difference is, though, that the Irish National Seismic Network stations are streaming in real time, so the data is coming in all the time. Whereas these temporary networks are sitting out in fields or sitting out in bunker installations, or sorry, not bunker, but like kind of small pits around the country in remote locations. And so, if you want to get the data, you actually have to go out there and pick it up off the instrument itself. So these data can be used to retroactively or retrospectively examine earthquakes, and to add more measurements of earthquakes into refine a location, perhaps. And it's the use of such networks then enables us to make a video like this. And so this is what we call a playback of an event. So this is an event from 6th of June 2012, D-Day, turns out. This was the largest earthquake we had detected in Ireland, and it's offshore. Magnitude 4, occurred just off the coast of Mayo, but we're going to see what it would have looked like if we had all these stations running at the same time, and as the waveforms start coming in. So this is an abridged version of the video. The video is actually about 2 or 3 minutes long, but just for purposes of bandwidth and for everyone that's dealing with dodgy internet, we've cut it down just a couple of seconds, but to get the idea. So what we're showing on the left-hand side are seismic stations. The triangles are seismic stations, and on the right-hand side is the streaming data coming in from them. So each of these lines, as we go down here, is a data feed from a seismic station, and the color coding on these triangles in the map indicates basically how strong the motion is, what is the amplitude, or how large the amplitude is of the signal on these stations. And the hotter the color, so the more you get to the red, indicates that these are larger amplitudes, and the colder the color, we go to green and blue, indicates lower amplitudes. So by looking at this map currently, we can see that there's large amplitudes to the west, and they tend to get smaller and smaller. They tend to decrease as we go east. And so as the colors get lighter and lighter, that means the amplitudes are getting smaller. So we've got something that's quite strong happening to the west. So even by the color coding itself, we can kind of guess that this event locates to the west of Ireland. So again, here, what we see is all the signals coming in, and you notice these red markers everywhere. So I showed you the seismogram earlier on, and this is where we have basically the change in the signal. So it looks like there's a flat line, and then all of a sudden some shaking happens. But if we were to examine what happened before this signal occurred, it would just be just a load more of oscillations. So it just looks like it's very, very small in comparison to what's after coming in. So we can't really see the fine detail here of what came before these red markers, because what's coming after them is such such larger amplitude. And so this has basically picked up a change in signal on many of these stations, and it's marked it in with a red marker, and it says a little P there to indicate that this could be possibly the P wave for the first arrival of an earthquake. So we'll just play this video to see how this plays out. So now this is data coming in, and now all of a sudden it has determined the location for it, and it's rearranged these stations in basically order of distance from the event, and it's made a location here, and this flashing red circle indicates that indicates the epicenter of this event. Here, these yellow and blue waves indicate then the kind of currently in real time where would the P and the S wave fronts be. Just to go through it again. So this is if this happened in real time, this is what this would have looked like. It would have seen the signal, and it would have basically made sense of it by doing lots of calculations, looping through many different possible hypocenters to see which one would best fit this this pattern we're seeing. Okay. So here again, I'll talk about some notable earthquakes. Again, this largest detected earthquake we had off the coast of Mayo. So it turns out it locates pretty much on top of where they have the Corrib gas exploration, and so this then does raise a few questions about what caused this earthquake, because we've had pretty much nothing since 2012. We haven't detected anything else out there, and there is another rule of thumb with earthquakes is that kind of basically if we had 1 magnitude 4 in a region, we'd expect to have 10 magnitude 3, 100 magnitude 2, 1000 magnitude 1. This is what's called the Gutenberg-Richter law for the frequency of occurrence of events. And so we've had nothing out there. The only thing we've had out there has been a magnitude 4 and an aftershock about an hour later from that event, which was magnitude 1.7. So it's quite puzzling as to why this one occurred. And also you will see on this map here, you can see that the coverage from angles, basically from around the earthquake, it's only covered from roughly about 120 degrees angle. So the remaining 240 degrees, there's no measurements made there. So that also affects the location of, or the location that we get. So what we actually get is an error ellipse, not an actual point. And also the depth value we get for it, we can't really trust too much either, because we have no measurements from 240 degrees. So we're not really able to say much about how deep it occurred, except that it occurred in less than 10 kilometers. And we do have a slight error in the kind of the east-west location of it as well, but not so much in the north-south. Below here then is a seismogram from a station that was about 70 kilometers away. And again, what we have before this signal is it's just oscillations again, and then we have something new that takes over, and it's much, much bigger than what came before it. So we can't really see anything that came before it in terms of squiggles. But we have this very strong signal that starts, and then a secondary, very, very strong signal. And what we don't see is anything that looks like, we don't see a third set of oscillations, or it might be a surface wave, for example. We don't see that if we do, it's not very clear. But this is basically your basic seismogram. What you normally see is something and then something else that's bigger. So it's a P and an S. It's very, very hard to see the individual oscillations, although you can kind of see them because we haven't zoomed in enough. But the next seismogram I'll show you is quite interesting, because this occurred, again, this is 2010. This was just before the era of the modern network, but this has been retroactively relocated. But whatever stations have been out in the country at the time, there was a couple of stations operating in the country. They weren't in real time, they were all sitting out in fields. But from what we're able to get from that, we're able to locate this. And this just off the coast of Dublin in County Clare. And this seismogram is very interesting because of a certain feature here. And this is, I can show you all of the earthquakes that we've detected in Ireland certainly for the past 10 years. And this is the only one where you're going to see this feature. And so this is a very interesting oscillation here. You can see actually make out individual oscillations. And the time scale is pretty much the same time scale as the previous seismogram, except this one, we have this signal here. And this is what looks like a surface wave in a seismogram. And what's even more interesting about it is that it seems to occur at different times on different components. So again, this seismogram is showing you the three components of motion: vertical, north-south, and east-west. So, and there's another seismogram I can show you for reference. This is a quarry blast from Arklow. And here, again, we see something quite similar. It's not as easy to make out, but there is something quite similar happening here. And this is what has been puzzling about this event, is that was it a blast or was it an earthquake? And so we do know that historically in Dublin they have been blasting at the pier, but I don't know how far back this goes, because again, I only started in Dias in 2014 and this event was 2010, so I've been trying to do some digging back on it. But it does look like that it could be a blast or something related to it, because it's a very interesting feature. The only thing that doesn't tell you it wasn't a blast is the time at which it occurred. So it was on the 6th of May at past 10 o'clock in the evening. So most highly unlikely that it would have been a blast. And also the magnitude of it, magnitude 2.6. This is quite large for a blast. So I'm not sure what is causing this, but maybe it could be they could have been blasting away in a pier, and then all of a sudden they had some kind of a collapse later on, and we end up getting a seismogram like this. But it's certainly a puzzling one. Next, we have the most recent felt event. And what's interesting about this is that in the past few years, we have been slowly improving our website. So our website is www.insn.ie. And on this website, then we have lots of information about what we're doing, about what we report on, but also if you feel something, you can actually then write into us and tell us about what you feel. And so again, this earthquake in roughly early April 2019, the next day we started getting lots of emails from people have filled out a form on our website, and I think it was about perhaps 130, 150 people over the of the next 2 days started to write in and tell us what they had experienced. And so then we were able to put all that together and then come up with what we call a felt map. And so there is a scale, there's called a Mercalli scale for a strongly won fields events, but we gave it a slightly our own scale between strong, observed, and scarcely felt and heard it. And so and this this map on the right, the star indicates the epicenter of the earthquake, a rough location of it, and then the all these yellow dots indicate the locations of where we got reports from people, and the color of those tells us kind of how intensely they would have perceived the earthquake. And obviously the darkest colors, the reddest ones, are roughly around Killybegs, so they would have been the closest. And as we get further and further away, quite doubtful that this would have been felt in Letterkenny. It was magnitude 2.4, so probably very locally it would have been felt. But we have plenty of reports from people, and it is interesting to see the way that the intensity of the feeling of the earthquake does roughly decrease with distance as you move away from it. And so this is obviously about 10% of the emails we got were lads having a laugh, messing around. So we had to exclude a lot of them, but it's quite interesting to be able to do this for the first time. And so this feature is there now, so we're able to do this continuously if people do feel earthquakes. Okay, this will be a summary of the last calendar year of what we would have picked up with our national network. And so on the left here, we can see lots of different things going on, but the interesting things to see is the red stars. These are the locations of the last the earthquakes from the last calendar year we would have picked up. The blue circles indicate locations of what we think are quarry blasts. The green triangles represent locations of actual quarries that we know or suspect are blasting. And then the yellow triangles would be stations. The pink and purple triangles then are stations of the British Geological Survey. And also we have we pick up lots of events in Scotland as well, and we can see a large cluster of them up here. This is a kind of a very large quarry in the middle of nowhere in Scotland. They tend to blast very regularly. So part of what I have done was implementing some way of discriminating between earthquakes and quarry blasts, and it's quite technical, so I'll leave that out for the time being. But what's amazing about it is that we can see that where we're able to locate these signals with such a relatively few number of stations, 7 on the island of Ireland and about another 10 then up on the British coast, even if they're able to see it. What we're able to locate and how accurately do they locate. So the quarries, we're able to actually locate them quite accurately, which is quite interesting. What we don't see here is lots of activity in Munster and in Connacht, and that's something we'll touch on a bit later on. And that's due to the number of stations perhaps we have currently operating. If we had more stations operating, we would probably see more things out there. Interesting enough about quarry blasts from an unrelated study, we looked at about 1,500 quarry blasts and about 100 earthquakes. And when we were able to plot when do quarry blasts happen, this is a histogram telling us here of hours, time of day. So they basically happen mainly between 9 a.m. and 6 in the evening. So the quarry blasts are pretty much, and mainly around lunchtime, actually, it turns out. This is generally when they tend to work. So it makes sense they don't blast in the evening or at nighttime, because the visibility is there. The red markers are basically distribution of when did the earthquakes happen, and it's pretty much, there's no preferred time. They seem to be kind of evenly distributed throughout the day, whereas they seem to be quite heavily concentrated for quarry blasts at lunchtime. The second graph here on the right, this is showing us the distribution of the magnitudes of the study. So it's about 1,500 quarry blasts, about 100 earthquakes. The distribution of magnitudes for earthquakes. Again, we have more small than we have large. We only have 1.4. We have something that's about 3.2, and that occurred offshore somewhere, far offshore. And most of it seems to be between the 0 to 2 range. That's where our earthquakes tend to happen. So magnitude 0, magnitude 2. So they'd be detectable up to about 200 kilometers, those type of, sorry, about up to 400 kilometers, the magnitude 2 earthquake. Detectable up to 400 kilometers. A magnitude 1, about 200 kilometers. A magnitude 0, smaller, about 100 kilometers. We have some negative magnitude earthquakes in there. They would have been picked up by kind of special means. I'll talk a little bit about later on. And some negative magnitude earthquakes will be absolutely tiny. And the vast majority of the quarries that tend to blast, they tend to be around magnitude 1.4, around that. So it's kind of the same type of magnitude all the time. In the previous calendar year, though, again, it looks quite similar. Less earthquakes, but a lot more quarry blasts. It was about 130 for the past calendar year. Go back to a year before that, we got 264. Again, very heavily clustered in the east and north. Again, that's due to the geometry of the network. But and one thing I looked at this year was, what about this year versus the past 2 years? This is quarry blasts being detected in Ireland, and this is telling us, red is telling us this year, blue is telling us last year, and green is telling us the year before that. So in 2020, we all know we're stuck in the pandemic at the moment, so that hit in March, and the number of quarries operating blasts we were detecting dropped way down. Normally it's substantially larger than that, but so we all know that happened in March. We went into lockdown, and so a lot of operations then, I guess, people weren't able to go to work, and so we ended up having an awful lot less activity being detected. And that does kind of segue into my next topic. I'll talk a little bit about seismic noise for a little sec. So this is now how to view seismic data another way. So what we're seeing is a full day's worth of data, and it starts off at the top. The red line at the top is the first 15 minutes starting from 1500, and then the green line underneath that then is the next 15 minutes. The gold line is the next 15 minutes. The blue line next 15 minutes, and then the next red line is now at 4 o'clock, and so on. So we kind of read it like you would read lines on a page, and so it just looks like nothing discernible inside here is the first thing I would say. And this is the raw recording of what we would pick up. And so this is, if we were to zoom in on any section of it, it all looks kind of roughly the same. If you're to count the time in between these individual oscillations, these individual peaks of oscillations, it's about 6 seconds, I think. And so this 6 to 7 seconds. This is so this signal we're looking at here that's dominating is produced by oceans. And this is a major phenomenon in Ireland, is that we get this, what we call microseism. And so there are two types, but the primary type that we normally get is basically the interaction of ocean waves with the ocean floor as the ocean starts to get, as the ocean floor starts to get closer to the surface, as we start getting closer to the coastline, we start getting it gets less and less deep. And so then we get this we get this signal picked up by ocean waves interacting with the surface, the sea floor. And so this is called microseism. And so this dominates what we see. So we want to get rid of this. So we apply a filter to our data to remove all of this. And then we see something like this. So this is more what we call high frequency stuff, where the oscillations are they happen faster. There's more per second than now. And so this is the exact same graph, but now after applying a filter on it. And what we can see is the amplitude. So it looks like the lines are thicker from 1500 down to about 1800, and the lines seem to get thinner from 1800 down to about 6 o'clock in the morning the next day, and then they start to get fatter again. And so the thickness of the lines is telling you the amplitude, how high the amplitude of what is being picked up by the station, and it seems to go down about 1800 and seems to go back up again at about 6 in the morning, generally when people start to operate. And this is again at a station in the Dublin mountains. So this is again not too far from motorway or from large road, also not too far from Quarry, and there's a house nearby. So a lot of what we're picking up is human activity on this particular station. And so another way to look at this is through this type of image now. So as we look vertically, we're looking at a time of the day, and as we move horizontally, we're looking at days. So as we go vertically, we get to about 6 o'clock in the morning, and all of a sudden this color changes to more lighter color and goes back to darker color again. So this lighter color indicates higher amplitudes, and darker colors indicate lower amplitudes. So for any given day, we can kind of see that, or it's actually broken up by weeks. We can see that there's, for most of the week, it's kind of quite high amplitude between 6 and 6 in the morning, 6 to the evening, and then drops down again. So this is again human activity. Roughly here we have Christmas time, so we have very little activity that's being picked up by the station. And then as we move along in time, along the x-axis, we get to here. And this is roughly the location of when they decided to close the schools this year. And here we have basically, then we have the lockdown starting, or the work from home happens. And so this pattern of large amplitudes from 6 to 6 to in the daytime seems to stop then at the end of March. It starts to pick up again then later on in the middle of, or towards the end of April. But this is something that we observed indirectly on this seismic station now, and I think actually it has been repeated worldwide. But this is an interesting phenomenon. So we ended up releasing a figure like this. This is again showing a similar type of thing. It's showing that the amplitude is basically has dropped down. The average amplitude is dropped down on this station, which is not far from, again, from sources, civilian sources of noise. Pretty much as we hit lockdown, it's kind of stayed quite low, and then it started to go up again. So like I said, there was a quarry nearby this station, so it started to operate and towards the end of April, and then that's kind of what seems to be contributing to the increase of the seismic noise. But it's an interesting graph, and it ended up making its way onto all these guys. We've seen this plenty of times before, Tony Holland, and up here we can see the same graph I was showing you has now been picked up by NEFIT, and they used it in one of the press conferences to tell people that they weren't adhering to the lockdown, because we see all of a sudden some kind of increase in average amplitude being picked up at this seismic station. So there was kind of a message to say to people that hang on, you need to stick to the lockdown. Now it turned out that it was mainly the quarry that was probably contributing to that. Very hard to say for sure what exactly it was. I mean, it could have been machinery at a house. It could have been many different factors, but it ended up getting propagated throughout media. Okay, there's one more thing I'd like to talk to you about with detecting earthquakes. This is something I had worked on a couple of years ago. So for all of these earthquakes on this map here, I picked one of them, one of the ones, this orange one here, and this is recorded at a station in Donegal somewhere, roughly here. And so this signal here, where we have a P wave and an S wave, these red lines indicate where I would like to basically cut this little section of data out. And it's like you just using this as a template to try and match other signals in data. See, can we find more of the exact same pattern? Because what we record continuously is a continuous signal, and I wanted to see, do we have any more of that exact signal in there? If we do have that in there, then we would basically have detected another earthquake of different magnitude or maybe the same magnitude, but this is how we would try to pick up an earthquake that looks identical to one we'd already know about. And so by doing that, I ended up, so down here is in red is this this little section that I would have cut out, and it's been squashed a bit, so it looks a little different. And the earthquakes in black then are ones that we did not know about until we tried to match that signal to what we recorded on that station. So that station had been recording for many years, so we searched all the years of data on that station for this signal, and we ended up finding, I can't remember exactly how many, but I think it was perhaps over 100 occurrences of this one, some of which we knew about, most of which we didn't know about. And so the one we knew about happened in 2012, 26th of January, sometime early in the morning. And then we started to find that this pattern occurred again and again and again later on that day. So we had more and more of the same earthquake happening. And so of different magnitudes, and occurred on the days after that, and then it started to occur months after that. What I haven't shown is that it actually occurred before this as well. There was many before this, and there was many several years after this. So we had what we call repeating earthquakes. It's the same seismogram gets generated by an earthquake over and over again. So this map now tells us the locations of where we have repeating earthquakes. These are happening over and over again, the exact same seismogram or almost identical seismogram. If the seismogram is identical, that basically means that whatever mechanism caused the earthquake is the same. So we have the exact same, almost identical source mechanism that's causing these earthquakes. So they turn out that certainly up here in Donegal and the Fana Peninsula, this one has a huge number of many repetitions of the same type of earthquake. This one here only contains, this cluster only contains 2. This was the earthquake we knew about, the magnitude 4, and we found an aftershock of that about an hour later. So out along the border, we have several places where we would have earthquakes regularly occurring within years apart, and down in Wexford as well. Certainly we have a couple that are recurring, again, with years in between occurrences. So a lot of the time, it's not really an aftershock sequence. An aftershock is generally a set of earthquakes that tend to happen directly after a main shock. And the time period might be anything from, hours to perhaps weeks, depending on how large it was initially. But these earthquakes are considered very, very small, especially the one in Donegal, magnitude 2.5 was the main earthquake we found up there. So huge number of repetitions of that. Very interesting. Indicates the same source mechanism. So the reason for that then is I'm not sure about the reason why we get them like that, but part of someone had said to me that it might be to do with this glacial rebound, that you have this very slow readjustment. That could be to do with it, but don't quote me on that. And also down in Cork, off the coast of roughly, I think it's Timoleague, or Cork McSherry, there was an earthquake in 2013 that was picked up there, magnitude 2, and so there's been quite a few repeats of that earthquake in the years since. I think the furthest one was about a year from that. Okay, so we have been focusing on local earthquakes and earthquakes that have been happening around Ireland, but of course, we know worldwide these are happening, especially on close to plate boundaries. So this is an example of magnitude 7.8 earthquake that happened there in July in Alaska. And the seismogram on the right then shows you what we would have picked up on the Irish National Seismic Network stations. And so this is now your classic seismogram. And if you look at the time scale down here, this is time scales in minutes. All the time scales I've been showing you before for previous earthquakes, for example, these times are in seconds. So the signal lasts much longer, and so this is indicative of how large the earthquake is. And so these are recorded at large distances, so we call them teleseisms. And here we can see that from these roughly 7,500 kilometers away in Alaska, have no problem picking up these signals. Generally, above magnitude 6 should be kind of seen on worldwide seismometers. So if you have magnitude 6 earthquake anywhere in the world, most seismometers should pick that up. Magnitude 7 certainly. Magnitude 8, magnitude 9, all these will be picked up on any seismometers in the world. Magnitude 5, then it gets a little bit more localized. Magnitude 4, more localized still. But we do record all these by, again, and it's very important to note these, to note when these particular, for example, the first blip we see here is the P wave arrival. This noting accurately times of when these arrive, these contributed towards global earthquake catalogs. And so these are basically, everyone uses them, so everyone contributes to them. Everyone records these times when they see these phases of earthquakes, large earthquake waves coming in. And there is a group called the ISC, International Seismological Commission, I think, and they're based in Britain, and they produce these kind of what would you call it, the gold standard catalog or seismicity catalogs. And then people are, this is like a primary input for a lot of people's research by recording global earthquakes. And again, up here, the black dots are earthquakes, the red triangles are stations. And so there's a huge number of stations, certainly in Western Europe and the US. That, by recording all of this stuff, we're able to then image the Earth. The more stations you have, the more data you get, the higher the resolution of basically an image you can create. So it goes from the local scale. If you have many stations, say within Ireland, you can do imaging of Ireland. If you have very few, then it's going to be hard to do something high resolution. So there is a group that uses measurements of large global earthquakes, and then they come up with they do imaging for the globe, and they come up with global velocity models. So these will have they will be able to kind of resolve structures on the orders, maybe hundreds of kilometers, or perhaps a little bit finer than that. Another part of what we do in DIAS, part of what I do, part of what my colleagues do as well, is that we're involved in monitoring of volcanoes. Certainly the director of National Networks, Martin Mulhoff, he's collaborates with people in Iceland, and the Professor Chris Bean. We have a collaboration with University of Edinburgh and Quito in Ecuador for monitoring volcanoes in the Galapagos Islands. So a lot of what we learn from Irish earthquakes, we're also able to apply to those situations, and vice versa. We pick up an awful lot of techniques by collaborating with people with different experiences. Seismic noise, of course, here you'll see that this is from Iceland, I think. This is monitoring of a volcano. All these little blips are earthquakes on a volcano, but in between that is seismic noise. And so this is something that is quite of interest in DIAS as well. And so there's currently a project, I think, is trying to image an underground river in County Clare or County Galway, I think. And so this will be done by measuring seismic noise very locally from within a field. So there are many interesting applications of all of this, but most of it is just having seismometers, deploying them, and seeing what you get. It's amazing what you pick up. The last thing that I would like to talk about is start flogging this a little bit, is that so the Irish National Seismic Network is partly funded by the Geological Survey. So they pay for myself and some of my colleagues to work on this. So on the left, we have basically the map of the streaming stations, the stations that are giving us data in real time. And what's being shown is basically the threshold of detection capability. What kind of magnitude can we locate where in Ireland? And so the colors that they go from light to dark indicates that you're increasing the magnitude detection capability. So that means that, the minimum magnitude we can pick up in, say, for example, in Antrim or in northeast coast would be around, certainly less than magnitude 1, but in Munster it will be much higher because of the distribution of stations that we have. That means that we're not really able to pick up weaker events in the west, versus in the east we're able to pick up much smaller events due to the fact that there are many more stations in the east, because we have all those stations in Britain. So they're very useful for helping us for picking up these things. So in the west we have nothing past Ireland, so our detection capability is not as good on that side. But theoretically, if we were to add in a few new stations, so these were on the right hand side, they're represented by red dots or red triangles. If we were to add in more stations, what would we be able to pick up then? And so this is a kind of an improved map, so we'd be able to pick up a lot more. Basically, we'd be able to pick up smaller and smaller events. Again, still it would be worse to the west, down Kerry and Mayo, but we greatly improved. So so the number of stations you have does kind of determine what you're able to pick up. And again, so this is one of the current things we're actually trying to do, is to build new stations. So we have plenty of sources of vibrations that contribute all the time to what's being picked up on these instruments. So it's not just earthquakes and quarry blast or anything like that. It's movement near the station. There could be the oceans. Wind is another important factor. Another source of noise is wind farms. Actually, they're quite bad for this, for seismic monitoring, because the vibrations transmitted by wind farms can actually travel quite far. And so it's about 5 kilometers is the recommended how far away you should be from this. But we're not quite sure on it yet, but it looks like as far as possible. So we are trying to look for new sites. And so we have a rough set of criteria of like how far we want to be away from all these sources of noise. They're listed on the left-hand side there. So oceans, you want to be about 10 kilometers away from the coast, certainly, because you get noise associated with that. Rivers and lakes, you don't want to be that close to it either. Wind farms, I've written asterisks beside it, because that's definitely one that we don't want to be close to. Quarries, again, if they're blasting quarries, you can have a lot of machinery grinding away, and so that can transmit to vibrations as well. There's a station in Wales, I think, and from about 6 in the morning till 6 in the evening, it's almost completely useless, because it's a quarry about half a kilometer away from it, and it's constantly operating. So it's dominating what's being recorded there. When you apply that criteria to basically the map of Ireland, so this is now showing the motorways, wind farms, quarries, all this. These are appearing as all these little dots everywhere. What's white is basically the space that's left over. If you restrict yourselves from 10 kilometers from all the coasts and from quarries and from wind farms, all of this, you end up with actually not a lot of land left over. So we'd be looking to put things in these patches that are left over. So we kind of did define roughly where we would like to have new stations, and so the green shapes there, rough locations where we'd like to have something in there somewhere from the point of view of improving our network. And the black little squiggles around here, the black bits, is telling us that inside those we have satisfied all criteria. We are far away from all the sources of noise as possible. And so one of the challenges for us then is trying to identify, okay, who owns land out there and who would be interested in having us put a seismometer there and perhaps build a new station. So that's what's been occupying a lot of our time, a lot of my time now for the past year or so. This is currently what we've got at the moment. So we do have a station in the Midlands, although it's very, very hard to find any outcrop in the Midlands. And again, with outcrop, we would like to be able to build on outcrop because we would have a good connection to the ground there. Bog is probably what we would like to avoid. And so up in Mayo, we're having a hard time trying to avoid bog, actually, it turns out. found a lot of places we'd like to put a seismometer, but we've already done quite a few tests. We put seismometers down. We found that, oh God, what we were recording is very, very noisy. And so we have found a place in Tipperary that's very good. So we're currently going to be building a station there. We've been scouting Cork recently, and so we currently have something sitting out in the field in Rathmore, instrument recording, and we have a couple of instruments recording up in Mayo at the moment. So I thought I would mention this if anyone is interested or knows someone in the West Cork area, that we would be certainly interested in trying to look down there, see if we can deploy something. I think that's pretty much what I wanted to get across. I'm probably been flying through it, but I guess with the summary of what I wanted to say is pretty much sorry, you just got a bit mad. Okay, so we've been operational pretty much since 2010. The modern seismic network has been. We're hoping to improve on that pretty much, but we are able to detect and locate earthquakes. We don't get a lot every year, but it is a function of how many stations you have out there. And so the more you put out there, the more you would hope to find. But it does look like that after 40 years of recording, we don't really see much in the interior of Ireland. Most of it's at the edges. Again, you wouldn't have known that until you would have put these things out, put seismometers out to record. A lot of what we do, the primary recordings, the primary data is maybe building up catalogs. That's one very useful thing from that. From catalogs, then people are able to build what's called velocity models. Velocity models then indicate then basically they're a way of imaging the what's underneath the ground. And more recent applications have been investigating seismic noise and on less explored areas. So that's pretty much what I wanted to talk about. So I think we're probably good to finish there. So I think I'll stop the sharing of the screen, and if people have questions, we can do that. So I see there's a thing flashing. So I'm going to go to stop share. Right.
Betty, do you want to say anything, or will I just go straight to questions?
Just before you do, just to say thanks, James. That was a real tour de force through what you're doing there in Dias. And just before Sinead maybe looks at the questions there, I just wanted to